Course objectives. Let's take a look at some of the basic goals of this course. 1. You'll dive into the basics of logic design, focusing on essential gates like AND, OR, NOT, NAND, NOR, XOR, and XNOR, and how they contribute to creating digital circuits. The course will guide you through designing and analyzing combinational circuits using Boolean algebra and Karnaugh maps. Advanced topics include circuit design with NAND and NOR gates, understanding hazards in combinational circuits, and exploring flip-flops used in sequential circuit design. You'll also learn about Mealy and Moore sequential circuits, state equivalence, optimization techniques, key timing considerations, and the role of tri-state buffers. You'll be able to apply these principles effectively to design and optimize digital circuits. 2. Understand the basics of hardware description languages, HDLs, and how Verilog is used to design digital systems. You'll learn to describe hardware designs using Verilog's core language constructs, including module definition, design hierarchy, and behavior description. The course will also teach you how to synchronize and communicate between different parts of a design using Verilog. Additionally, you'll learn the rules for using identifiers, comments, and whitespace in Verilog code, ensuring you can effectively describe and configure simple designs. 3. Discover the different Verilog data types and how to represent values accurately in your designs. You'll learn about logic values, nets, and registers, along with the rules and examples for declaring these types. The course also covers vector declarations, handling truncation and padding, and defining literal values. You'll learn to declare nets, variables, arrays, and module parameters, enabling you to manage values efficiently in your designs. 4. Get to know the various Verilog operators that allow for precise control over your design. This includes bitwise, reduction, arithmetic, shift, relational, logical, and conditional operators. You'll also learn about concatenation and replication operators. You'll be able to apply these operators effectively in your Verilog code to implement accurate and optimized designs. 5. Learn to describe design behavior in Verilog using procedural statements. The course will cover procedural blocks like initial and always, as well as event control blocks to manage execution timing. You'll explore procedural assignments, branching statements, if-else case, and looping statements, for, while, repeat, forever. These tools will help you effectively describe and manage the behavior of your Verilog designs. 6. Understand the differences between blocking and non-blocking assignments and their appropriate use in different scenarios. You'll learn about continuous and procedural assignments, understanding their impact on simulation and design behavior. This knowledge will help you make informed choices, ensuring your designs are accurate and efficient. 7. Delve into the Verilog simulation cycle to understand how it affects code execution. You'll learn about procedural blocks, different types of assignments, and event controls to minimize risks of indeterminacy and race conditions. The course also covers synchronization techniques, including level-sensitive and delay controls, helping you write reliable Verilog code for simulations. 8. Learn to use Verilog subroutines, including functions and tasks, to make your code more readable and reusable. Functions help simplify logic by performing calculations and returning a single result, while tasks can perform more complex operations. You'll also explore common issues such as static variables and argument passing, ensuring you can efficiently manage code complexity. 9. Discover how to control and optimize the compilation process of your Verilog code using compiler directives. You'll learn about text substitution, conditional compilation including external files, setting simulation timescales, and applying pragmas. These directives will enable you to manage the compilation of your Verilog source files more effectively.